So through 1.9 we kind of looked at different aspects of limits, and a lot of the work was focused on algebraic manipulation and how we can solve for limits, as well as identify limits from graphs and tables. So that was kind of what our quiz was about. We take somewhat of a shift here in the unit. We still use limits, but we start talking about continuity, which hopefully rings some kind of bell. And the only limit calculations that we'll do that are new is infinite limit. So instead of saying the limit as x approaches some real number, it'll say infinity there. Okay, and I think those are kind of interesting in some cases. So that's coming up. We do, this unit has 16 sections, and this is 10 that we're starting today. So we're about halfway through. Okay.
Oh, the infinity stuff was on the quiz, right?
Yeah.
Question.
There's like one.
Yeah, there was one question.
Correct. Oh, that was the last one.
And that's the one you probably have to grade, since it should just be able to do it.
Okay.
We had, like,
I'll look at it. If I had a question on there that we didn't get to, I'll take that into account. But, yeah, I'll look at it. So continuity, you see the word let h be a continuous function. What do you know about it at this point?
It didn't have any holes or like asymptotes or something.
Okay, no holes, no asymptotes.
The range is
Well, it could be continuous on an interval instead of the whole real number system, but so sometimes, like, here's kind of what Trevor brought up. Maybe we have a graph that does, I don't know, I'm just making something up, but something like this. And if we restrict the domain of this, maybe to -10 to 10, well, it is continuous on that domain or on that interval, but not over the whole course of the function. So yes and no to Trevor's comment about it being the domain being -infinity to infinity. Could be, but it doesn't have to be. Describe what you see when you see a continuous function. If I showed you a graph, what do you look for?
solid line.
Okay. Yeah, right, like a solid line. So that's important to know. In fact, you can't really do this problem without reading that word. It's the most critical word in there, or at least one of them. So with that, now we have to go back to our definition of limits and know what the continuous word is telling us in kind of in sequence with the limit. So it says limit as x approaches 9 from the left is 2. So I'm just going to sketch out some rough points here. So coming in from the left, this thing could do something like that, right? So far, that's all we know. But because it says continuous, what does that mean about the rest of the graph? Like, could I have this happen? Okay, so we know that doesn't happen. And I do encourage you to draw a graph sometimes with these because it helps you think through what you're given and how that relates to the choices. Okay, could it do this?
No.
Why?
It's continuous, a whole perfectly
Yeah, it's continuous right there, and that would be a discontinuity. So that means at 9, even though we're coming in from the left, to be continuous, I have to have a point defined there at 2. Like I can't jump up here to something else. Okay? And then it has to keep going in order to be continuous. So once you have that graph, now we can look. So limit as x approaches 9 from the right. Well, yeah, that has to be 2. Otherwise, it's not continuous. So that's good. H of 9 has to be 2. Otherwise, that was the case I just had a second ago with the whole. So that has to be true. Limit as x approaches 2 overall has to equal h of 2. That's basically what we just said with the previous 3 statements. So that has to be true. And then D, well, who we have no clue what's going on over here at 2, right? Like that's pretty much completely unrelated. So That one is not guaranteed. It could be true, but it is definitely not guaranteed. So how'd that one go? As a kind of summative limit idea here. Give me a thumbs up if you got it. Okay. So this is kind of a little bit preview of what we're getting into. So let's grab those note packets. It's 110. And it's on types of discontinuities. This is gonna, honestly, it's gonna feel like a review of Algebra 2. Maybe Pre-Calc 2, but definitely Algebra 2. So we're not to that packet yet, but just have it ready because it comes right after a few of these slides. So function f has a removable discontinuity at x equals 5. Which of the following could be the graph? So don't shout this out. Just be ready to raise your hand. We'll do it this way, like 1, 2, 3, 4 is A, B, C, D. Okay? So which of the following could be the graph of f if it has a removable discontinuity at 5? And it probably depends somewhat on if your pre-calc teacher talked about removable versus non-removable. So, we'll see. But all right, everybody vote. Which one do you think it is? So you're holding up like A, B, C, D. A is 1, B is 2, C. All right, so most of you. All right, most of you are actually no. It's kind of split between 1 and. Well, between A and D. So D is correct. So start kind of, as we work through these next couple, start developing what you think the definition of a removable discontinuity is. So basically the two main choices were A and D. Why would this one be removable versus that one? So start thinking about that. Okay? All right, let's look at the next one. This one tells you that these three are non-removable, and that one is the only removable one. So hopefully that refines your definition a little bit. So I'm just pausing to let you think about like, why would D be a removable discontinuity? What is different about it than the others? Okay. All right. Limit as x approaches 5 of f exists. Which of the following could be the graph of f? So the limit exists. So we'll do the same 1, 2, 3, 4. Okay, go ahead and vote. Okay, so people are saying 4. Why doesn't it exist here? It's an asymptote. It's got an infinite discontinuity. It approaches infinity as we get closer to 5. Why doesn't the limit exist in B and C? They're not the same, right? Remember the language we used was the two or the one-sided limits agree. And these don't. So one-sided limits don't agree. This one is infinite. Okay, so I'll just erase that and use the word. And then so that one is the only one that has all the criteria to say the limit exists. So it's also the only one with a removable discontinuity, but can we have, I'll save that question for later. All right. If the limit as x approaches 5 from the left and right are distinctly different real numbers, which of the following could be the graph of f? Distinctly different real numbers, which of the following could be the graph of f? So you're going to do your vote thing again. Alright? So limit from the left and right, left and right, left and right. It's these two, right? Okay? Why is this one not it?
Because they're not real.
They're not.
It's not real. And of course D, the one, it's the same number, so. Alright, which of the following is /r continuous? Be careful with this one. I put this note in red down here. Okay. This one's definitely a different level than the others we've done. And the reason why is because it's kind of going back to what I said when Trevor talked about the whole real number system, is something can be continuous on its domain without being continuous in the entire picture. Okay, what is the domain of, by the way, this function is a rational function. It's not this one, but it's some version of 1 over x. Okay? Remember 1 over x was this graph? So whether or not, like from one side it goes to positive and the other side goes to negative infinity, that's okay, because what is the domain of a function like that? Is 5 in its domain? No. So is it continuous elsewhere? So yes, it's continuous on its domain. I'm going to abbreviate continuous with conc, on its domain. Now, does that one surprise you? We just got done saying like it has no limit or whatever. We can see a clear gap. So is it surprising that we can say it's continuous if we add the clarifier on its domain? Okay? So that last part that I wrote is huge. Because if you didn't put that, is it true? No. Okay, how about this one? Is it continuous on its domain? Well, what is its domain? Like, especially if we put arrows just so you can say what its domain is. Does the domain of this one exclude 5? No, because there's a point right there that's on 5. Okay, so the domain does not exclude 5. Is it continuous? No. Because it's discontinuous at 5. Discontinuous at 5, let's be specific, at x equals 5, and 5 is in its domain. Okay, with that said, let's look at these last two. Is C continuous on its domain? Ocean says yes, some of the rest of you say no. What is the domain of C? You guys remember how to write domains with interval notation? Okay. So if we wrote the domain of this one, it would be, well, do you know interval notation? Is that what you used to use? Okay, you can also do set notation. I'll do interval first. So negative infinity to 5, union 5 to infinity. So is 5 in its domain? What do parentheses mean?
Does not.
Doesn't include it. So is this continuous everywhere else but 5?
Yes.
Yeah. So this is continuous on its domain. How about this one? Well, its domain.
Staff, we need to do a medical shelter in place, Shelter in place, this is for medical.
So we're good. So this domain is negative infinity to infinity because we do not exclude 5. So is it continuous on its domain? No. Because 5 is included, but it jumps right there, or it has a hole. Let's use that language. It has a hole there, okay? Is this confusing a little? Or are you doing okay with it? Okay? I will encourage you, if you don't remember domain very well, remember it's all x values that the function uses. So like this one, it just skips over 5. Everywhere else, it's just a nice smooth curve, but 5, it just kind of skips over because we have an asymptote there. So 5 is not in the domain. Okay, so these two are continuous on their domain. Kind of interesting twist. You'll have to keep an eye out for that. Do some review of domains. All right, I'm going to go back to this first, second slide. Can you define what a removable discontinuity is at this point yet? Okay. I'll make it easy. If you can just plug a hole, it's removable. So let's talk through that. Can I just plug a hole here? No, because I have one up there as well. Here, can I just plug a hole? Nope, because there's 2. And here, it's not even a hole, it's infinite points, right? I would have to plug. So those kind are not removable. So back to your paper. Not all that stuff, sorry. The basic idea, at least visually, of continuity is do you have to pick up your pencil. So this is smooth. No, you don't have to pick up your pencil. Now, let me write that better. In calculus, we define this a lot more, way more clearly than just do you have to pick up your pencil. But graphically, it's the same idea. Maybe say broken or missing piece or something. Even a hole counts as that, right? You have to like skip over it and draw the next section of the line. Okay, so types, we have a hole. So that's removable. That's the only one that is. We have a jump. Actually, let's save it for the last one, since it's in order this way. So we have a vertical asymptote. That is non-removable. I'm going to write that off to the side in a second. And then we have a jump discontinuity. Another name for vertical asymptote is infinite discontinuity. So if you hear that, that's what it's referencing. So do you recognize these from Algebra 2 and Pre-Calc? We didn't do, this is called a piecewise function, and we didn't do that in Algebra 2. I don't know if you did it in Pre-Calc. Do you guys remember doing the piecewise ones? Yeah, I don't think so. Okay, off to the side maybe. These are non-removable. So removable, maybe just to make sure this is gonna stick, plug a single hole. And we'll have a section where we learn how to remove a discontinuity. In other words, plug the hole. And so that's coming up, but we're not gonna do it today. Just know today that that's what a removable discontinuity is. Okay, here's some examples of how you'll do this. It says for each function, identify the type of each discontinuity and where it's located. So we've got to do both. So type and where. Well, what do you think? How do we do type? How do you decide if it's a whole vertical asymptote or a jump? You guys remember that? You technically have done it. Well, at least the first two you've done.
It's about the numerator and the denominator.
Yeah, what about it?
If it's a denominator ever, the zeros of the denominator are wholes.
Sort of.
Are, if you can cancel out,
Okay, there we go.
if you factor and cancel out something from the top and the bottom.
Alright, so this, first of all, we need to know that we're looking for rational functions. With zeros in the denominator. Like, let's say I just put up, I'll let you write this, but what if I just put up this function? Do I need to worry about discontinuities in that? What kind of function is that? It's just a parabola, right? Shifted up, it's continuous, there's no worries, there's nothing causing trouble, let's say it that way. So when we have discontinuities, it's because there are mathematical issues in like a denominator or under a square root kind of idea. So anytime you see one of these, what's your first job? Factor, yeah, so let's factor this thing. Are you guys good factors?
Devin's pretty good at it.
He's good at it? He loves factoring?
He hates it, but he's pretty good. I always do that.
Okay, so go ahead and get that factored out. And Trevor was kind of alluding to this a second ago about, well, I see a common factor in the numerator and denominator. Do you guys remember what that means? That's a whole, right? So we have a whole there, but that still leaves a 0 in the denominator. Where? At x equals -5. So let's talk through that. Any duplicate factor? And the top and bottom, we're going to go informal. Obviously it's numerator and denominator, but this is fine. Is a whole. So any duplicate factor in the numerator and denominator, top and bottom. Okay, in this case, where is it?
2.
Yeah, the factor is x minus 2, but what's the whole?
X equals 2.
Yeah. Okay, x minus 2 gives a whole at x equals 2. What did we do to get the 2 from the x minus 2? Just solve the 0, right? So x minus 2 equals 0. Let me raise this up a little. X minus 2 equals 0. Okay, so we have a whole. Is that removable or non-removable? That's removable. Okay? Are we done? No, because we still have this 0 right here. We have another 0 at x equals, let's set it equal to 0. I'll just remind you, hopefully that's a quick pickup. So here's, and we're not going to write all this out for every one of these. This is kind of the notes part. Any uncancelled zeros in the denominator are vertical asymptotes. And so they are non-removable. Okay? Does this ring a bell? Like, you definitely saw it in Algebra 2. I'm sure you saw it in Pre-Calc early on, probably. But okay. So in summary, it says identify type and where. And where am I going to write it is the real question. Maybe I'll just do a little bubble out here on this one. Okay, so in summary, we have a hole and just say removable at x equals 2. And can we agree to abbreviate VA, which is non-removable at x equals -5. There's our summary. Sorry, I have it jamming up this next problem. Okay, why don't you try number 2? Just like 2 minutes, just to get your. All right, so we're factoring again. Let's do a different color. If you notice, this is difference of squares. So x squared plus 1 and x squared minus 1. And then that x squared minus 1 is also a perfect square, so we can factor it again. X squared plus 1 doesn't factor. Okay. So notice we have a duplicate factor, top and bottom. So what is there? At x equals what? -1. Remember, we find the 0. We solve for the 0 of that factor. So x plus 1, that's a duplicate factor. And then what else do we have? So a vertical asymptote, non-removable. This time I'm going to write infinite. Just to remind us that's an option. Okay, we have an infinite discontinuity where? At 1, because it doesn't cancel. And then what about this guy? If you find the zeros of it, what do you get? Can you solve for the zeros in your head? Okay, let me remind you then. If we set this equal to 0 and we just do our little algebra, what happens when we square root a -1? Okay, we're square rooting a -1. So we get plus or minus I. Okay? This is not real. No discontinuity. So that factor doesn't matter in the sense of the discontinuity. We ignore it. Alright. Any questions on that kind? How'd you do? Did you get all the way to the end on that one? Anybody? Okay. That's okay. We're just learning. Alright. I'm gonna try to work through this one with some kind of speed a little bit, but there's kind of a lot going on. Why? Why do you suppose? Remember, we're trying to find places where the denominator equals 0. So what happens in one of these kind? Is there a denominator for tangent? What is it? Yeah. So I don't see a denominator. So no denominator. Let's rewrite. So this h is actually sine 2x over cosine 2x. Okay? So what are we looking for to find the points of discontinuity? Which are tangents. We know tangent is like this weird graph that has lots of them, right? You guys remember that? Looks like this. So there's lots of points of discontinuity. How do we find them? What has to be true about this guy for us to know where those are? Somebody say it. This is a big idea. We're looking for the zeros of the denominator. Okay? Let's, at the top of your, like we can't have this lost. If you get anything from this lesson, this is it right here. So I'm putting it at the top. Discontinuities occur at zeros of the denominator. Right? If the function is smooth sailing and it never has an issue, then we don't have any discontinuities. So we need to find zeros of cosine 2x on the interval given above, which is 0 to 2 pi. So now you need to know your trig circle, right? Your unit circle. Where does cosine have zeros? Just cosine. Say it.
Pi, 2 pi, 0.
That's where sine does.
Oh.
Yeah, good job.
Pi over 2.
Pi over 2 and 3 pi over 2. Okay. Cosine has zeros at pi over 2 and 3 pi over 2, and its multiples. Actually, let's say their multiples. If I could write it correctly, sorry about that. Okay, so our job is to figure out where this guy, this cosine, has zeros. So we're setting 2x has to equal pi over 2, or 2x has to equal 3 pi over 2. Oops, I forgot an equal sign. There we go. Okay, everybody following why? Because the argument of the cosine, that's what's inside of it, has to be pi over 2, but it's actually 2x. So solve this little guy for x, right? Well, x equals, if I divide by 2, that's going to be at pi over 4. Over here, that's going to be at 3 pi over 4. Okay, but am I all the way up to 2 pi here? No, I still have to keep checking until we get all the way to 2 pi. Right now I'm only at 3 pi over 4. I'm not even like halfway around. Okay? So let's go back around the circle. We have pi over 2. What's the next one if we go all the way back around? So this is, you see what I'm saying? So pi over 2 plus 2 pi is what? Okay, that was one we just solved for. Come back around to it, hit it again. So that means add 2 pi. How many halves is 2 pi? How many halves is 2 pi wholes? That didn't make sense, right? So it's pi over 2 plus 4 pi over 2. Okay? So also at 5 pi over 2. And I'll write that it's pi over 2 plus 2 pi. Okay, so we came back around and hit it again. Okay, so 2x equals 5 pi over 2. Divide by 2, that's going to be 5 pi over 4. And at this point, maybe you can see a pattern. Where's the next one going to be? Like if I come to here and add 2 pi, that's going to be 7 pi over 2. right? And at 7, 2x equals 7 pi over 2, or x equals 7 pi over 4. And then after that, do you see how we're going to hit 2 pi? We're going to swing back around and be outside of our interval. So we have 4 places where this thing, between 0 and 2 pi, we have 4 places where it has a vertical asymptote. Cool, right? Cool, but frustrating because you have to account for all of those. Alright, and then finally, look at part 4, number 4. Tell me about it. No denominator. So do we worry? This is continuous. So we don't have to worry. No denominator. In fact, let me just put that sub note right there. So it does help if you know your function, like parent functions and their appearance. It helps on that somewhat. So in terms of the paper tonight, do the evens and then the whole test prep section. So like 2, 4, 6, 8, 10, 12, and test prep.